Hello, good morning, and welcome back to MUSC110, Introduction to Audio Technology. I am your host, Dr. Clint, and I will be taking you through the next installment of this series of video lectures. Today, we will be focused on this topic, psychoacoustics, or how we hear, how our bodies do the hearing. Last time we were speaking about the physics of sound, and I want you to be thinking about those concepts as we look at what is actually happening physiologically when we hear sound. So as a reminder, we've been talking about sound as a periodic wave of air pressure. And we looked at what we called a waveform, one of the most fundamental concepts in this class. And the waveform is a way to visually represent this pattern of air being pushed together and pulled apart, wiggles in the air. Now, we're going to go from, and so the wiggles in the air are the sound. We hear different aspects of the sound based on how the air is wiggling. So if the air is wiggling back and forth an extreme amount, it's very loud. If it's wiggling just a little bit, as far as how far the air molecules are displaced from rest, it is quiet. So a lot of displacement in the wiggle is loud, more pressure, right? So if the air molecule is displaced more, it's going to push against us more. If it's very quiet, or if it's not being displaced very much, it's not going to push as hard. So the more pressure that a sound event contains, the louder it is. The more that air is moving back and forth, the louder it is. The speed at which the air is moving back and forth is frequency, or how high or how low it is, or pitch. So you could still have a loud, high sound. The air molecules would be displaced the same amount, but they would be displaced at a faster rate. We also talked about how high sounds and low sounds travel at the same speed. So this is something that can be confusing, that we have a rate at which they're wiggling back and forth, and we have a rate at which that wiggle is moving through space. So we covered all of that. We also covered sounds happening at the same time. So you have two different sounds happening at the same time. They're going to cancel each other out, or they're going to, sometimes one wiggle wants to push while the other wiggle wants to pull. And so you get some more complex waveforms that aren't just those simple sine waves. We also talked about how acoustic sounds, like a string or a drum, for example, have multiple waveforms happening within them, because the energy is bouncing back and forth from one side of the resonant body to the other, creating different timings, sort of different patterns of different wave patterns within one string. So as an example, let me just show you a couple of GIFs. So like if you were to, here's a nice shot of somebody playing a guitar. And you can, just by looking at this, you should be able to tell what are the high strings and what are the low strings. So the faster vibrations are going to be the shorter, the shorter waveforms. So the string on top is sounding higher, and I know that because I can see that there are more complete cycles of the waveform within this frame than the string on the bottom, which only has a couple. But you can also see that these are not perfect waveforms. These are not like very smooth sine waves. It looks like there are waves within waves. And strings do that, and pipes do that, and drums do that. And the reason is the energy is going back and forth across the string, and it resonates on whole numbers, and that's what we call the harmonic series. I'll get more into that in a second. So today I'll be talking about how all of these pattern, all these, the frequency, the loudness, the harmonics, the phasing, all of that gets into our brains. And I promise to be much more brief on this in this lecture. I went through the review of the previous lecture because these two are very much connected. So really what I want to answer in this portion, the psychoacoustics, your introduction to psychoacoustics, or how we hear, is really it's translating all of the physics, the patterns of the wave patterns and all of that. It's how that all gets translated into what we hear. What happens when all this stuff reaches our body. So I am relying on our knowledge of the basic physical definitions of this stuff in order to create a physiological definition of all this stuff. So here is the anatomy of the ear. I'm going to start here. Sound pressure waves enter our bodies. Well, they sound pressure waves affect our entire bodies. We register sound perceptually as it enters our body through the ear canal and reaches the tympanic membrane or the eardrum. And then it goes through this whole other process. So this is a nice diagram to give us the whole sort of system all connected together. And I'm going to step through and look at each of the components. The reason I'm doing this is we're going to be able to make connections between the physics of sound, how we hear, and this is going to be important when we start learning about how microphones are designed, how speakers are designed, and to understand the differences between different audio formats, because there are certain limitations to what we can perceive as humans because of this physiology. So here is the whole system. We have the canal. This is sound coming through. It hits the tympanic membrane or the eardrum. In here, this is like the auditory tube. There is air in here. This is sort of connected to our nose and throat. Then this connects to the cochlea here, which is which is connected to the auditory nerve, which then connects to our brain. So let's dig deeper into each component. So when you hear eardrum, when you hear tympanic membrane or eardrum, and I'm sure that everyone has heard of the term eardrum before, it's actually a really useful metaphor because our eardrum acts exactly like a drum. Now, I have these two GIFs here to help us understand what's going on with vibrations or waves traveling, resonating a surface. So just like a string, you see a string on the left, and it's being bowed. And you see that wave pattern going back and forth from one end of the string to the other. And that creates, like I said, these harmonics, these different portions, different ratios of the length of the string. The same thing is happening when we play a drum. So you look at the right over here, I have a drum. Now, the energy is put into that drum head from where the drumstick strikes the drum head. That energy, just like in a pond, ripples out to the rim of the drum. And then that energy comes back into the middle and ricochets around the edge of the drum, okay? Now, you can tune a drum in all sorts of ways. As you can see around the rim of the drum, there are all these places where you can tighten the drum head. And so you could you can tune drums so that they are a very specific pitch. or you can tune them in such a way that it's much more complex, so that the different tightness of the drum head around at each point where you're tightening it creates different pitches, and then it creates more of a noisy, interfered sound. So here we see this drum, and when it's struck, it resonates. But the thing is, like a speaker, and we'll learn this later, a drum can work in two ways. It can be a way to resonate, to create sound. It can also be a way to collect sound. So our eardrums are like drums that work in reverse. So the vibrations in the air, the sound pressure waves, the wiggles in the air are entering the ear canal here, you see, and they are wiggling the eardrum. So the eardrum is wiggling in the same exact way that the air is wiggling. And that is triggering, these two really tiny microscopic bones that are then connected into the cochlea. Okay, the important thing to emphasize here is that the eardrum is wiggling in the same exact way that the air is wiggling. That wiggle is then being transmitted through these little bones that are then connected to, so here we see the eardrum wiggling, and we have these two bones, right? And these bones are then sort of pushing and pulling against the cochlea. So here we see the cochlea. It's like this snail shell looking thing. And it's the I guess you could say the doorway or the mouth of the snail shell is connected to those bones that are being pushed and pulled by the wiggle of the eardrum that is wiggling along with the air. Now, within this snail shell, there is, it's filled with fluid. So just as a reminder here's the eardrum, here are those tiny bones, and they're connected here to one end of the snail shell. This is all filled with fluid, and in this fluid, there are these cilia, which are these tiny microscopic hairs. And those tiny microscopic hairs are all connected to little nerve endings in the auditory nerve. So as the air wiggles the eardrum and the bones push and pull against the mouth of this snail shell, the liquid inside of the snail shell gets waves. There become waves within this liquid, right, that are ebbing and flowing along with the push and the pull of the eardrum. And the little hairs are sort of swaying in the breeze. So these little cilia, these little hairs are swaying in the breeze of this fluid inside of our cochlea, inside of the snail shell. And as they sway, they send little nerve impulses along the auditory nerve. Okay? So now, one thing about, say, listening to very loud sounds, so stuff that is above 120 decibels, there's so much pressure that is created that sometimes the pressure can push down some of these tiny little hairs, these cilia. We have a whole bunch of them. There are a whole bunch of them. But that pressure can sometimes push them down, and they just get stuck. And that can lead, obviously, to hearing loss. So the fewer hairs you have, the more difficult it is to perceive differences in how fast the fluid is moving back and forth, or how fast the wiggle is, right? So that's why when we lose hearing, we lose the higher sounds first, because higher sounds are moving faster. So if we have higher frequencies, which are faster waves, more waves per second, then we need lots of hairs to be able to be able to tell the difference between those different waves, those different fast waves. So when we start losing our hearing, we lose our high frequencies first because we're losing little hairs inside of our cochlea, which is part of our hearing system. And this concept will become really important later because it has an analog in when we talk about the difference between, for example, an MP3 and a WAV file. But we'll get to that next week, I think. So once these little hairs get tickled by the waves, they send neuronal messages. They send nerve impulses along the auditory nerve, which is connected directly to the brain, and it is all processed within the primary and the secondary audio cortex, which are sort of on the side and kind of underneath the top layer of gray matter. This is where those wiggles are turned into sonic images. So the wiggles are processed in a way by our brains into what we perceive as sound. So up until this is an important thing to remember. Up until it goes down the auditory nerve and reaches our brains, it's just sound. It's just air pressure. It's just air pressure. It becomes sound once it is processed in our brains. And that's why, thinking back to that graph that I showed that compares the frequency range, perceivable frequency range of different species is important. So a bat's brain is a bat's physiology, and a bat's brain is wired so that it can hear all these high frequencies, but none of the low frequencies. So the world sounds very different to a bat than it does to us. And that's been selected for through evolution. Okay, so that is really tracing the sound from its really, let me just kind of go back through this one more time. From the point where it's sound pressure, right? It is air pressure. It's no longer air pressure, right? Now it has entered the auditory system. Now, once that tympanic membrane is converting it into wiggles of a bone, then it becomes wiggles within the fluid inside of our cochlea. It is no longer air pressure. It is going through a process of conversion that eventually becomes nerve impulses or neuroinformation. Now, there's another aspect to the physiology of hearing. So we've just kind of gone through the ear and the brain very quickly. But of course, when we are in any space, if you think back to when we're talking about causal listening, Michel Chion's 3 modes of listening, and he brought up causal listening, and that's the type of hearing that you do where you're able to, where you just immediately recognize the cause of some sound. And it's often not connected to being, it's something that you didn't even see. So our brains, when they are listening, when they are trying to process cause, are actually listening to multiple things at once. And this is what we call reverb or reflections, or how we hear space, the space in which sound happens. So here we see a useful diagram of how this really kind of works. There's a speaker on a wall that, say it's my voice talking to you. So that speaker is sending out waves. Now, those waves are going in all sorts of directions, all sorts of angles. They emanate, like I said, like ripples in a pond. So as sound waves, you're going to have the direct wave that has the shortest distance to travel. that is going to reach you as a listener first. But like I said, these are ripples, right? So as I guess the shortest distance will reach you first, but as this ripple goes out, it's going to hit the floor, it's going to hit the ceiling, it's going to hit walls, and it's going to hit them at all these different points. This results in you hearing the direct sound first, and then a fraction of a second later, you hear a first-order reflection, and a fraction of the second later, you hear the third-order reflection, and so on. So when we are hearing sound, unless we're listening on headphones, you're hearing all of these reflections, and that's allowing you to locate the source in space. Now, think about how different acoustic spaces are designed, like concert halls versus classrooms, or your bedroom versus your closet. These different spaces have different spatial characteristics. And the differences have to do with size, they have to do with the materials that they're built out of. And we hear those differences in the way that sound is bouncing around the room. And one of the ways that we do this is being able to judge these microsecond differences between when the sound arrives at us. So here's another diagram to reinforce that this is happening three-dimensionally. These diagrams, here, right, you've got floor and ceiling, but it's also happening off of all the walls. And, of course, it's bouncing off of the walls at different times, too. So it's this very complex situation that is completely three-dimensional. And so now, another thing that I should point out is as sound bounces around the room, it loses energy. So direct sound is going to be the loudest. First order reflections are going to be a little, going to be quieter. Second, quieter. Third, quieter, et cetera, et cetera. Eventually, the sound just loses energy, right? Like it's not going to bounce around like a pool ball forever. Eventually, it runs out of juice. So this is one way in which we are able to judge these differences. One is a timing thing, so when the sound hits, the first thing that hits us, we're like, okay, that's the most direct. But the other thing is a relative amplitude thing or loudness difference. Now, the other way that our bodies play an important role in all of this, it isn't just our ears and it isn't just our brains. Our bodies are also incredibly important aspects of listening, of perceiving sound. First off, think about going to a very loud concert. One of the important effects of that sound is that it's physical. It's especially the low bass at a really loud concert. It's not just that you hear it, you feel it. You literally feel the air pushing back and forth against your body. You can feel maybe like your jeans push back and forth, or the hairs on your arms tickle as if they are like the little hairs in your ears. That's because, again, sound is air moving back and forth. And so when it's amplified to a high degree, we can perceive that then, not just in our ears, our very sensitive ears, but in our less sensitive skin all over our body. So we do, in that sense, hear with our entire bodies. It just so happens that our ears have developed to be much, 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 much more sensitive to changes in air pressure than the rest of our bodies are. The other way in which our bodies play a part in hearing is that we use them perceptually to make judgments of where a sound is happening in space based on reflections. So what research has shown is that part of the way that we can locate a sound in space, like if some sound happened in the room and you were able to know, oh, that's just behind, like you didn't see it, but it's to the right and just behind me. Part of the the reason that we're able to do that is because, one, you have a general sense of the space that you're in, and you're already accustomed to it, and you're making judgments about how the sound is bouncing off the walls around you. But even just as importantly, we also make judgments as to how the sound is bouncing off of our shoulders and how it's bouncing off of our earlobes. So if you know, if you can discern that a sound is happening behind you, that's because you're making judgments about how the sound is bouncing off your shoulders and bouncing off your earlobes. And it's bouncing off of those two parts of your body differently than it would if the sound was happening in front of you. So we are making incredibly impressive micro judgments of timing after we have sort of learned in early life, when we're just little, kind of figuring out how to perceive the world. This is one of the things we learn. We learn through experience how to make judgments about space based on how fast the sound is and the way in which the sound is bouncing off of our own bodies. So to wrap up, the psychoacoustics of hearing, the human perceptual system of hearing, is incredibly sensitive. We can hear frequencies from about 12 hertz or 12 cycles per second all the way up to 24,000 cycles per second, which is, compared to most other species, just about as impressive as it gets. There are a couple that have a larger range than us. We can hear loudness levels from a sound pressure level of 1 all the way up to 10 billion, trillion. And again, if we could hear anything any quieter, we would be able to hear changes in temperature. We can also, so we're talking about the speed of the wiggles. We're talking about the relative pressure of the wiggles, like how far the air is being displaced from rest. We can also perceive, like I was just pointing out, reflections or delays, you could think, that the amount of time that it takes, the amount of time between the direct sound and the reflected sound of about 2 milliseconds apart, which is incredible. That's 2/100ths of a second apart as two distinct sounds. And this is how we're able to locate sound in space as it bounces off the wall, but even more importantly, off of our bodies. So we use our bodies, and this, this ability is demonstratable because you're able to figure out where that sound is pretty much like in all sorts of different acoustic environments. You could be outside, you could be inside, you could be blindfolded and kind of figure it out. So the reason you're able to figure out where that sound is emanating from, maybe in a room that you've been blindfolded and brought into, is because your perceptual system is making judgments about that sound and how it's bouncing off the room around you, but more importantly, off of the body that it has been trained to create a timing map to, which is really kind of crazy and cool to think about. All of these... each of these are we're going to be talking about as soon as we open up software. We're going to be dealing with frequency, we're going to be dealing with loudness, and we're going to be dealing with delay. So it's important that we know on a very fundamental level how we perceive these things, and it will help us to understand how that is being replicated within software. Okay, I did it. I got through this whole thing in a much shorter time. Next time we meet, we'll go over this and make sure that it's all clear and have a discussion about all of these topics. And I look forward to that discussion next time I see you. Have a fantastic weekend.